references from neighboring components in the design. What this will do is create a pocket for us that stays related to the size of the core blocks. So, okay. Now, one of those specific mold functions that I mentioned was for cold runner designs. Runners are created by driving a profile shape along a sketched path. And our design today really doesn't have the need for a long runner, but I can show one to show how the function works. So the dialog that is showing now, it offers a choice of runner sizes. And because of the curved parting line here, I think we're going to choose trapezoid shapes. The numbers are adjustable, of course, to whatever's needed. Now the runner that gets modeled will be used as a cutting object solid. So it's going to intersect with any of the other mold components that the runner path crossed over. So here's a look at a typical result. Next on the list to discuss are inserts. Most molds have inserts of some sort. The catalogs that we mentioned, they have core pins and other standard parts, but sometimes inserts are custom to one area. And Cimatron has developed a fastening tool for breaking these out as new parts in the assembly. For example, on our core, this tall area here in the center is an ideal spot for a replaceable insert. And I'll only need to define that area, and that's something a quick sketch can take care of. Now, you recall that the core block is an open model. Big holes in it. And we simply don't worry about gaps unless there's a good reason to. Well, here I'm going to use a solid technique for creating the insert. So beforehand, I am going to request to stitch together one area of the core block. This is an example of Cimatron letting our design needs dictate the course of action. I only need to worry about the geometry that's right in my current working area. So an insert function, in the insert function I need to pick the block and the new shape to cut from. And I'm also going to specify in the tree where the new insert part goes, and then just set the depth of the cut. And this will break out our new piece. Insert 1 is here. You see all that's left in the core block is a pocket. The insert itself is all new part in the assembly. An insert like this probably needs a screw to hold it in place, as does a core block for that matter, and that's going to bring me back to standard catalog parts one more time. You can save a lot of time with a well-built catalog library. But even better, our catalog assemblies of many parts at once. The Add Mold Component Guide is a shortcut to thousands of catalog parts within Cimatron. And at the moment, we are looking at the DME catalog. Amongst all the standard things that we can use here is a DME unit lifter assembly. Because we really can't forget that undercut area that's still left in the core. Now this type of adding parts we'll call add on a face. And all we need to do is pick the anchoring face for the lifter unit. And then we want to make sure that we have a reference point from the relevant geometry in the cavity. So once the parts are on screen, that's when we can deal with adjustments to the size and the positioning a little bit. This unit needs to be turned around. And then we can also add a dimension. In a catalog group like this, the important sizes in the individual parts, they're called out as leading dimensions. And because they're purchase parts, the leading dimension dialog only allows you to choose from the sizes that are actually offered. Now, also in this add operation, I want to note that we're adding with cut. Okay? What it means is that these parts already know what holes and what pockets they need to install in the surrounding plates. So I'm going to section the job a little bit to show the cut results. You see pockets in the ejector plate, holes for the screws. All of this comes out of the catalog. In Cimatron, adding parts also add the pockets, which saves a lot of time for the user. Now the cuts have gone so far as to make the lifter pocket in the core block as well. And I really have to be careful here not to get too much of a good thing. Because I need some of that geometry in order to create the face on the lifter. What I'll do then is step backwards one feature in the history tree of the part. See, I can manipulate the timing of the cut by using the tree. So that lets me do operations in any order that works the easiest for me. Now, because of Cimatron's ability to work so well on the open solid sheets, here in the lifter, all I really need to do is bring in a bit of geometry that will give me the required shape I want. Okay? And the next choice will be a cut function. And cut understands how to trim off the lifter blank. And it can even delete the surfaces that we use for the cut after it's done with them. Remove cutting object. So that creates just the lifter we need. The only thing that remains is to go back to the core block and bring the history there back up to the current level. Well, lifters help eject, but most molds have some sort of ejection system with pins. And here again, Cimatron has a special set of functions that really help to speed up the process. What we're going to do is go back to the catalogs one more time. This time, place some ejector pins. Now, there are an awful lot of sizes for ejector pins. It's a big table, and what we can do is sort the table to make things a little easier to see. Also, we'll ask that the system calculate length. What it can do is measure the distance from the ejector plate up to the core, and you'll know exactly the shortest pin you can choose out of the catalog. Now, this time, while I'm adding parts on face, I'm going to ask for the snap grid to be on. A lot of users like this. Well, for ejectors or other components that can be placed at nominal numbers. And we'll drop a few in there. Now, for our purposes here, note that what we're going to do is leave the cut without cutting the holes. Because for ejector pins, there is a special type of hole available. This is done by ejector pocket. What ejector pocket can do is look at every pin. And it's going to see where it's going to break through the core block at, and then back figure of the reamed hole size for a constant fit length. And there are other drill options there too. You can, well, rather than have a set fit length, you could choose to have a set clearance length, or no clearance drill at all in the core blocks. Whatever really the shop standard is.
So this here is basically looking at the high point or the low point or the midpoint of the intersection of the pin to the surfaces, and then coming back, I think you put in a 1/2 inch. So you're going to have a 1/2 inch of fit on your pin here. Doing some pretty intense calculation there.
Another dynamic section to see what Ralph's describing. Cimatron also has developed a function called Ejector Trim. Now, Ejector Trim saves an incredible amount of time in mold design, because in this one function, you're going to ask it to act on all of the pins, and it trims the tops off right at the top of the core block surfaces. The system knows the structure of the mold assembly. It understands where ejector pins have to stop at. Okay. Designing cooling channels is another mold task that Cimatron helps to automate. I'd like to show a simple example of that now.